Hello students, and welcome to the section 4.1 lecture on ecosystems and communities. So for these notes, and this is what you'll turn in today as your homework for required practice, please take out a piece of paper. So there's no template for you to use, you're just going to write these notes out by hand. But as you do so, I please want you to follow the format that you see in the notes. For instance, if I skip a space, then you should skip a space. If I indent with the idea, you should indent with the idea as well. Outlining your notes helps keep it organized on the paper, where you have like a heading, a subheading, and then details. And then having those spaces, having those indents, having those breaks also helps keep the notes organized in your brain. So the organization on the paper translates into organization on your in your brain. So please don't just write out everything in paragraph form. Follow these formats. All right, so this is the only section we're testing on for this particular unit, chapter 4.1, Ecosystems and Communities. So what's the big idea? The big idea is there's a complex interdependence within nature. Abiotic and biotic relationships shape these ecosystems. Abiotic is non-living, biotic is living. And again, you may find it helpful to pause the video from time to time to get these notes completely recorded. And again, the real value in notes. Yes, note-taking in and of itself is a learning experience. Students do learn things from taking notes initially the first time. But the real value in note-taking is coming back to those notes after you take them. So take the notes today, right? Take a picture of them, submit that as your assignment. But then as we lead up to the test, within 24 hours, you should spend 5 to 10 minutes reviewing the notes. And then a couple of days later, spend 5 to 10 minutes reviewing the notes. We want to move this information from your short-term memory to your long-term memory. So it's not enough just to take the notes, revisit them on a regular basis. All right, so this interdependence in nature, it's an interdependence that is not necessarily a positive negative relationship in the sense that think of predator-prey relationships. Predator-prey relationships are very violent, very aggressive, not necessarily very peaceful, but there still is this interdependence within nature. Sometimes, you hear this interdependence in nature and you think, oh, it's, I'm going to go down to the pond and the music is going to play and I'm going to sit really quiet and the flute's going to come along, or the deer is going to come along and get a drink of water as the flute music plays in the background. Interdependence does not necessarily mean they get along. There's a lot of violence in nature. The scale of death in nature is horrendous, and a lot of that death is really, really, really unpleasant. But that doesn't make it any less interdependent. All right, so let's keep going. Some questions to consider as we take these notes. What is climate? What's the difference between climate and weather? Then how do climate and weather affect organisms and ecosystems? So really, ecology is all about the relationship between living and non-living world and the relationships among living things. And again, if you need to pause from time to time to get this all written down, then please do so. All right, so let's compare weather and climate. And what's the difference between the two? Weather is always a hot topic here in Minnesota because we know that it can change from day to day. So I'm recording this lecture on a day when we broke all previous temperature records. It's November 3rd today, and the high today in Minneapolis was 75 degrees. A week ago, it was in the the high 20s, and there was snow on the ground, and that was in October. All right, so what's the difference between weather and climate here in Minnesota? Both involve variations in temperature, precipitation, and other factors. All right, so temperature, we know what that is. Precipitation, that's rain, snow, sleet. Weather are our day-to-day conditions. Today it was 75 degrees. Last week on Tuesday it was in the high 20s and there was snow on the ground. Weather, day-to-day conditions. Just write down the weather today. The day that you take these notes, write down the weather. In all likelihood today, it could be in the 60s or 70s. It could be in the low 40s. It could be rainy outside. It could be sunny outside. That is weather. Climate is our average conditions of temperature and precipitation year after year. So climate is averages. Climate is averages. Climate, average conditions and precipitation year after year. Okay, so my wife and I went on our first date on March 8th in 2000. So it was the first week of March, and we ate at a restaurant in St. Paul, and we ate outside on the patio. It had been so unseasonably warm that we had patios in restaurants open up all over the place. It wasn't just warm that day. It had been warm for like the week and a half leading up to that day. Normally in March, the first week of March, it's cold, it's snowy, and you're certainly not eating outside at a restaurant. A couple of years ago, we had a snow day in the third week of April. That doesn't happen very often. So those are those weird weather things that sometimes happen. But on average, it's cold and snowy in March, and it's warm and humid in, say, July, right? So weather, day-to-day, climate, long-term, pretty straightforward. All right, so we're going to look at 4 factors that affect climate on this planet. The number one factor. So 4 factors that affect climate on this planet. The number one is solar energy, the amount of solar energy that we get. This is the main source shaping our climate is the sunlight hitting the Earth's surface. Okay, so how does this work? Some of the light that we get from the sun bounces off the atmosphere and goes back into space. We're going to see a picture of this in just a second. Some of the light is absorbed and converted into heat. So some of that light escapes into the atmosphere, gets into the atmosphere, and is trapped as heat. All right, so some of that heat radiates out of the atmosphere and goes back into space. And it's sort of weird to think about a giant planet radiating heat in the way that you radiate heat, but it does. And then lastly, some of that heat is trapped in the biosphere, right? And that trapped heat is what determines Earth's average temperatures. Right, so again, I know this is sort of a lot to write. If you need to pause it, you certainly may do so. Some of the light is reflected back into space. Some of that light gets into the atmosphere and gets trapped as heat. Some of that heat escapes. The heat that doesn't escape is trapped in the biosphere. Some of that is in the atmosphere. Some of that is actually in the ground. And this trapped heat is what determines Earth's average temperatures. So that's the solar energy, the number one factor determining climate on this planet. There's going to be 4. The second one is the greenhouse effect. Now, the greenhouse effect gets a lot of conversation now because of global warming. Students oftentimes have the misconception that humans created the greenhouse effect. We did not. It is the greenhouse effect that makes life on this planet habitable. The reason we are not a giant ball of ice or super seething inferno is because of the current effect of the greenhouse, or the current effect of the atmosphere and the greenhouse gases. All right, so what exactly is this? There are 3 main gases that trap heat in the atmosphere. There are a few others, but the 3 main ones that we're concerned about are, you can probably guess, CO2, carbon dioxide, Another one is water vapor, and a third one is methane. We'll spend a little bit more time on carbon dioxide here in class, on the in-class day. All right, so 3 main gases: carbon dioxide, water vapor, and methane. They trap heat in the atmosphere. These gases act like a blanket or like a greenhouse. They let the light in, and that light gets converted into heat. And as gas levels rise, so do temperatures. Think about, you say it's July, and you are in a shopping mall on a hot July day, or you're out with friends or whatever. You come back to the car, and it can literally be like 120 degrees inside the car. It's because all of those windows are acting like a greenhouse. They let the light through. That energy, that radiant energy, gets converted into heat, and then the temperature in the car comes way up. The atmosphere on the planet does the exact same thing. It's gases that act like a greenhouse, trap the heat, hence the term, the greenhouse effect. We're going to draw this picture in just a second, but we're going to see it in a bigger slide. All right, so here's just a picture of a greenhouse. Again, I can't stress this enough. The greenhouse effect is a natural occurring phenomena. If it wasn't for the greenhouse effect, we wouldn't be able to live on this planet. But what we do know is that humans, by burning fossil fuels, are adding CO2 and methane to the atmosphere, increasing the effectiveness of the greenhouse effect. So yes, the planet is getting warmer because of human activity and carbon dioxide mainly. But the actual greenhouse effect is a natural occurring phenomenon. Right, so how does it work? I want you to pause the video here and draw this picture. You don't have to draw this. And again, there's no points. Before you pause it, just listen up. Like, there's no points for saving paper. Draw this relatively big so you can put in the labels and the arrows and have a nice, clear, neat picture. So just go ahead and take a minute and pause and draw this. All right, so now that we've got it drawn, let's just take us through what it means. All right, so again, here is our sunlight, right? Radiant energy. Some of that light is literally bounces off the atmosphere and goes back into space, right? We just wrote that down. So here's the light. Here are those greenhouse gases. Here's the carbon dioxide, the water vapor, the methane. Some of that light gets through. Some of that light is converted into heat, right? Some of that heat radiates out and escapes, right? Some of that heat is trapped in the atmosphere. This is the light that gets converted into heat that stays trapped in the atmosphere. It's like a tiny, tiny thin blanket over the entire planet that keeps us nice and warm. To give you an idea of how effective carbon dioxide is as a greenhouse gas, take 2 planets besides Earth. We have Mercury and Venus. So in this order from the sun, it's the sun, Mercury, then Venus, then Earth. You would think, because Mercury is so close to the sun, that it would actually be hotter than Venus. Venus is further away from the sun than Mercury is. But the surface of Venus is actually hotter than the surface of Mercury. And this is why. Mercury is so close to the sun that the radiation from the sun blasts any semblance of an atmosphere off of Mercury. So Mercury has no atmosphere. It's just a small rock screaming around the sun. Venus is far enough away and big enough that there's enough gravity to have an atmosphere. But it's an atmosphere that is mostly CO2. Because CO2 is such an incredibly effective greenhouse gas, the surface temperatures of Venus is something like 750 degrees Fahrenheit. So the surface of Venus is actually hotter than the surface of Mercury, even though Mercury is closer to the sun, because Venus has an atmosphere that gives it the greenhouse effect. All right, so again, it's this. Now, again, with humans burning fossil fuels, we are making this thin blanket of CO2 thicker and thicker and thicker. It is really important for the exam coming up here that we understand this picture and exactly how this works. All right, so that's a second factor, right? We've got solar energy, right, as the one. The second, which is all the four factors affecting climate. Solar energy is number one. The greenhouse effect is number two. A third factor affecting Earth's climate is the relationship between latitude and solar energy. All right, so sunlight hits Earth's surface more directly as you move from the polar regions towards the equator. Another way of saying that is to state that the light is less direct or a more oblique angle as you move from the equator towards the polar regions. We're going to see this picture enlarged in just a second. I don't think this picture does it justice, so we're going to see a big one here in just a second. Again, if you need to pause to get this all written down, then please do so. Putting these little hyphens, underline the terms where I have them. All of these are little tricks that help organize the information and keep them organized in your brain. The same amount of sunlight, because Earth is round. I mean, that sounds silly. Why wouldn't Earth be round? But because Earth is round, the light hits and goes around the curve. What this means is that the same amount of sunlight heats a larger surface area as you move away from the equator. We'll see it on the next slide in just a second. The change in light intensity equals heat and temperature variations. The change in light intensity equals heat and temperature variations. All right, so I bet if you asked mom and dad, why do we have seasons in Minnesota or on planet Earth? There's a good chance that at least one of your parents is going to say, oh, it's because we're closer to the sun in June than we are in January. And that's not actually the case. We are actually closer to the sun in our orbit in January than we are in June. Earth's orbit is not a perfect circle. It's more like a oblong or egg shape. But the difference between how close we are to June and July is not the real reason why we have dramatic seasons. The real reason we have seasons is because of the tilt of our axis. Because we spin, so here's the axis. We don't spin like this around the sun. We spin like this. We have this angle, which means that in the wintertime, the Earth is leaning away from the sun. And in the summertime, the Earth is leaning towards the sun. I think the next picture will demonstrate that quite nicely. Okay, so there's nothing to write here. Just look at this picture and listen to the explanation. Here are 5 bands of light from the sun. But notice they're all the same thickness. They're all the same thickness. So it's the same amount of sunlight coming from the sun. But notice here, see how thin this band is? This is the most direct light hitting the Earth. It's almost at a 90-degree angle. So here, this amount of sunlight heats this much Earth as the Earth spins from day to day. But if we go up here, this same amount of sunlight has to go around this long curve. So here we have the same amount of sunlight between here and here. But here, this amount of sunlight is heating a much larger patch of Earth. Well, if we have the same amount of light heating a larger patch of Earth, that energy is more spread out, which means that there's less energy per square meter, per square foot, and so the temperatures are cooler. Same thing going south. As you go further and further away from the equator, the angle of the light becomes more oblique. This is about where? So we're about 45 degrees. This is the equator. Here's 90 degrees up here. Here's the North Pole. Minnesota is at about 45 degrees. So we're right in here somewhere in terms of the angle at which the light hits our ground. So in the summertime, when we're leaning towards the sun, we have a lot of light heating a smaller patch of Earth. In the wintertime, when we're leaning away from the sun, that same amount of light is heating a larger patch of Earth. So this is the reason why we have, there's temperature this graphic shows the reason why there's temperature variation going from the equator north or south, because we spin at this angle, and sometimes we lean towards the sun, and sometimes we lean away from the sun. That changes the angle at which the light hits the planet, and that's what actually gives us our seasons. All right, so again, just to recap thus far, we're looking at the 4 factors that affect climate on this planet. 1 is solar energy, 2 is the greenhouse gas and the greenhouse effect, number 3 is latitude, the relationship between latitude on the planet and the amount of energy it receives, and then here's this last one. This is the one that we're probably least familiar with here in Minnesota, because we're about as far away from the ocean as you could possibly get, but large bodies of water, like oceans, have a huge impact on climate, worldwide climate. Uneven distribution of heat from the sun causes wind, and that wind causes ocean currents. Water absorbs a lot of energy, and as that wind starts to move that water around, that energy in the form of heat moves around with it. Now, you don't have to memorize any of these maps, but what this map is showing is different kinds of currents. We have surface currents that are cold, surface currents that are cold, and then other currents that are deep. So because we have wind and because we have uneven distribution of heat, that creates different pockets of air temperatures, which causes wind. That wind then moves the water, and that's what causes major currents. And then as those currents move, they transfer large amounts of energy all over the planet. As wind and water move, they transport and distribute that heat unevenly. All right, so to recap, 4 factors that affect climate on this planet. The amount of sunlight that we get, the effect of the greenhouse gas and converting that sunlight into heat, right? The fact that Earth is round and that light hits Earth at different angles depending upon where you are on the planet, and the Earth's orbit affects the angle at which the light hits the planet depending upon the time of year, and then heat transport caused by the movement of both wind and ocean currents. The 4 main factors that affect climate, the long-term weather patterns on the planet. As always, if you need to go back and review, please do so. I hope this was helpful.